I'm assuming by now folks would have understood what P4TC is or have a little bit more better background. So in this talk, we're going to focus primarily on the control plane driver aspects of it. We're going to talk about a control plane driver that is more P4 compliant and that is capable of offloading functionalities to a target device, uh, which understands P4 using P4TC classifier. In this talk, we are going to touch briefly on the runtime control, how the existing classifier works, how they can coexist peacefully, so on and so forth. So starting with the motivation, why would anyone want to do an offload? So straightforward answer is it helps with the performance, saves CPU host, it helps with the latency, and for this specific case, it helps to bring P4 programmability into Linux kernel space. So we are going to go over the driver architecture overview. I'm going to take a sample P4 program as an example. For anyone who is new to P4, the way to read a P4 program is table is a keyword, L2 forward is the name of this table, and every table has a key and action. In this example, the key is of we're doing an exact match on destination address. An action can be drop or send. Actions are elaborated over here. These are the send to port and drop packet are very well known and well documented externs in PNA architecture. And the apply section is where we we specify the flow of the pipeline or how these tables should work together to create a certain output. So here in the apply section, we say that if the Ethernet header is valid, we want to apply an L2 forward table. So step number one is to write a P4 program for a pipeline that one wants to offload it to an IPU. Step number two is to compile. For compilation purposes, we have two compilers. One is an Intel IPU specific targeted compiler, and the second is a P4TC compiler. Both serve different purposes. So the Intel IPU compiler is going to generate a binary blob. This binary blob contains data plane initialization information in the form of a binary and plus some context information which acts as an helper for the driver. We're going to get into the details of it in just a bit. And then there's a P4TC compiler. This P4TC compiler generates two files. One is a JSON file and another is a template file. The JSON file, as the name says, it's for introspection purpose. It's for validating the rule and the entry information that comes from the admin or the SDN controller. And then the template file is a bash-like conversion of the P4 program. So just to summarize, step number one is to have the P4 program. Step number two is to have the IPU output and then the P4TC artifacts. And then we take this binary blob, since we are focusing only on the offload aspects of this for this presentation. We take the binary blob, we load it onto IPU, and once this binary blob is loaded, visualize it like an empty table. An empty L2 underscore forward table is created on IPU and it is ready for the rules to be installed. How this binary is consumed, we are going to get into it in the later slides. So now the stage is set. So admin can program a rule. As soon as they add a rule, it's going to be handled by the P4TC classifier code. And since ICPF driver is a module, is a kernel module, the kernel code is going to generate a callback that we call NDO setup TC. This NDO setup TC is an entry point to the driver for any CRUD operations. And this NDO setup TC will talk to a thin layer of code that we call ops handler. This ops handler will do the job of converting the kernel structures into something that is more P4-like, into something that is more abstracted away but before programmable layer that we call pipe manager or pipeline manager. The job of this pipeline manager is to facilitate all the CRUD operations, resource management related to the table activities. It is uh, P4 programmable layer, but still abstracted away from any device specific details. So this pipe manager now has all the information that came all the way from the admin. It's going to hand it that information to something that we call LLD layer. This LLD layer is very specific for a given device. It'll have the code for initialization, reset, and configuration of a specific device. Pipe Manager hands over the key and the action to this layer, and this layer, in this specific example of a rule add, is going to use IPU config queues to actually program the rule all the way to Intel hardware. So now we can visualize that the L2 forward table has the rule that came all the way from admin. Now, to complete the picture, this driver will also support the port representer and switch type compatibility. So that's the high level view of how from a given P4 program all the way how we offload a specific rule. Um, so in from this diagram, I'm going to touch on the rule portion of it, the CRUD portion of it. We're going to explain it line by line in a demo that comes towards the tail of this presentation. And then I'm going to focus on how the package, which is one of the prime information about a P4 program, is consumed by the driver. So let's start with the runtime control. Uh, so anyone who is not aware of the P4 or is only having the TC background, uh, so the only differences between an existing TC infrastructure and P4 is the control block where we specify the flow or how the tables are stitched together. So that was something that was missing in the traditional P4 TC. So to make anything P4 compatible, there are two attributes which are very, very important. One is the pipeline ID, table ID, and another is action ID. So on the left side is the kernel structure, the information that kernel gives about a given rule to the driver. And on the right side is the target independent abstracted away P4 programmable layer, our pipe manager. The interface to pipe manager looks like. So here I want to emphasize on the pipeline ID that is indicative of a given P4 pipeline instance because there can be many instances. IPU supports having multiple pipeline instances. And then there's a table ID that is indicative or a pointer to a specific table to identify a specific table in a given pipeline. And there are key and action attributes. So these are the things. One more important thing to note that is we can get into any we can get into the details of it, but the introspection file and the context information over here, the way these two informations, the way these two files are independent. One is consumed by the user space. The introspection file is consumed by the user space. The context file is consumed by the kernel space. But the key similarity between these two files is the table ID, the action ID is going to be exactly the same that facilitates and helps with the handshaking between the user space and kernel space when they point to a specific table or they talk about a specific table. Next, I'm going to briefly touch on how the package is actually downloaded. So in our demo that comes later, we are going to walk over how we add a queue disk, how we add a filter, instantiate a P4 pipeline, and how does the rule look like. But for the scope of this slide, the TC filter add command is when we instantiate the P4 pipeline. Let me go over it in a little bit of detail. So anytime we get the driver gets a TC filter add request, the kernel infrastructure is going to register a callback with the driver. The driver, on registering this callback, is uh, going to a is going to consider the string, which is a p name, and trying to and go to a well-defined or agreed upon location, look for that file, extract two key information from the file. The driver is going to parse the context information and keep it live for the life of a P4 program, and it's going to parse the additional metadata and the additional data plane initialization information to the hardware. If there's a success, then this message is navigated all the way back to the kernel. So that's the flow, and the elegant portion of it is with just one command, a tc filter add command, we are facilitating two important things, which is instantiating of a p4 program in the software and in the hardware. So I'll hand it over to James to go over the rest of the topic.
Now I'm going to talk about what we're working on to support TC Flower. As you know, TC Flower is an existing TC filter that can be used to set up flow level rules given a set of keys and actions that are defined through the TC Flower. So this is a little different than what P4TC tries to do, which is to set up different tables of a hardware P4-driven hardware pipeline, not necessarily a flow. But P4-driven pipeline can also accommodate TC flower rules, and that's what I want to talk about. So here is pretty much similar to the P4TC picture that Nia shared. Difference is that you can see that the TC Flower ops handler is going to map to the pipe manager that Nia talked about, and the mechanism of downloading the package and the context JSON can be done through the dev link. Another option would be to download it through the TC P4, but there would also be an option to download it through the dev link. So that's what this diagram is showing. If we can go to the next slide. Now, so the goal is to be able to support TC Flower control plane without any changes and have it mapped to P4 programmable pipeline. So just to remind the audience, P4 programmable pipeline is a pipeline that is independent of whatever the P4 is going to be running. So the mapping of named protocol like TC Flower to a program independent pipeline requires a mapping of named fields that are in the TC Flower onto the model driven fields of a P4TC pipeline. So we plan to have a table that helps with that kind of mapping. So the primary work of that kind of library is going to be to extract the TC Flower key and action and map it to P4. And the mapping is extracted from the context JSON that was discussed, and it is model driven. So the model is going to be embedded in the context JSON that we extract from the metadata file that we get. And certain P4 parameters like a pipeline ID or table IDs are extracted from the file, and that is used to map onto the pipeline instantiation. If we can go to the next file, this diagram is showing visually and kind of what we just talked about, which is there's a mapper function in the handler, NDOT setup handler. And that mapper function is set up through the parsed context.json info that is fed through the context.json file. And when that is set up at the initialization time, then when TC flower requests come, then parsed fields of the TC flower is used, fed into the mapper, and mapper is the one that does the mapping onto the pipe manager interface. And the pipe manager interface is a P4 defined interface. So, so mapper is really the dynamic entity that once P4 program changes, mapper is able to adapt to the new P4 program, while the TC flower interface itself and control plane can remain the same. If we can go to the next slide. Yeah, this is showing example of how that mapping is done. And that mapping is done through something called P4 annotations. And P4 annotation is just a notes that can be associated with each lines of the P4 program. And in this case, so we're showing a P4 table here with the two key fields, and each of the key fields has an annotation. And first one is showing the key Ethernet type address to be the sort of the protocol header of the first field, and the field value to be the destination address. And so once the mapper, what mapper would do is once the key Ethernet address is received, and looking at the second parameter as well, that once the source address of the Ethernet header is received, address is received, looking at those two fields, it knows that that flow TC flower request maps to this table, and the actions would map to one of these P4 actions given here. In this case, it's a drop and send. So once you get a flow action of drop, then it will map to P4 drop action. And once you get a flow action redirect, then it could map to some like send P4 send action. If you can go to the next slide. Yeah, so this one is showing now sort of coexisting pipelines where a part of the pipeline is based on the P4TC, defined through P4TC, and another part is implemented through the Linux bridge. So in this kind of case, then the control plane is totally independent. So really, there is no, even though they're sharing common pipeline in software, the orchestration needs to make sure that the sort of different parts of software pipelines are controlled and owned by either P4TC or Linux bridge. So as long as there is no crossing over of provisioning, then really things can work seamlessly and rather independently. So if we go to next slide, this one is also showing an example of even for the mapping of SwitchDev FTV handlers, how those kind of calls can also be model driven through the P4 annotations that I talked about. So in this case here, this table is, if this table is going to be mapped, it's got a VLAN ID and the destination address, and the VLAN ID mapping to of a VLAN ID from the ATV add to device call to this P4 table is done through the annotations that you see there. And similarly, mapping of the destination MAC address is also driven through the annotation that you see there. So, yeah, uh, so this is also done through the annotation mechanism. And to speak a little bit more on this, we can have a kind of scenario where you can P4 TC allows you to hook onto the ingress TC and another P4 program onto the egress TC. So you can set up ingress TC for HCL and then go through the FTP to find the destination the destination port, and then you can go through the egress TC for something like a metering. So, control plane. Speaking of control plane, same for representers will be applied to both of the P4 TC pipelines, and then to add it to the FTP instance, and separate independent ingress and egress P4 pipelines could be instantiated in this case. And P4TC and bridge control provisioning just happens independently. In terms of data plane, because they're acting as independent software components, there need not be any really any metadata, extra metadata that needs to be carried between FTP and P4TC pipelines. Now, there could be more tightly integrated scenarios of P4 hardware P4 TC sending up some metadata information to the software pipeline and have some information be re-injected into the hardware pipeline. So in that kind of case, then there could be extra metadata that gets carried along with the packets. So we're currently exploring the options of how that can be done. And these are the things that we are currently working on. So next, I'm going to hand off to Nia and Wei Chan to talk about our demo.
So continuing on the uh, CRUD operations that I had talked about in the beginning of the presentation. So here we are going to show you a demo. It's a simple firewall NAT scenario. Primarily, we are going to focus on the source NAT. There is an elaborate demo in the breakout session if anyone is interested. So in the source NAT, the packet coming from the intranet will be modified to an IP address and send it out on the internet. So that's the requirement. In this example, what should happen is at the top of the screen, the source IP address 192.168.0.1 should be modified to 10.10.10.10, which is in our case the outside world. So IP was acting like your gateway. Uh, I'm going to quickly skim over the P4 program. And so in this P4 program, we have the E forward table and I forward table, egress and ingress. Both are quite identical. I'll touch on one of them. In the E forward table or egress table, we match on the source IP. We want to do an exact match on the source IP, and we perform an action called TX mod index. On the left side, we see the TX mod index getting elaborated a little bit. In essence, what is happening in this action is we're applying another table called mod source IP table. In this table is where we match on a specific index, and we modify the IP address. So the things to note over here is things like vendor metadata. So vendor metadata, as the name implies, it is target specific, and different. This point mod block pointer will be different for different vendors. This is something that will work on IPU. And next, I'm going to play a recording, and Rachel will speak over it.
Okay. Now we have a full screen showed up on the full terminal showed on the screen. The white one is uh, it's a TC mount. We're going to monitor the TC activity. Yeah. The green one, mostly we're going to enter the command. Then we can see we already insert a ICPF kernel driver. Then also we see the ICPF driver has been inserted correctly, and that device it's 1453. It's an Intel device, the IPU 2100. So we go into the simple net demo directory, which contain two files, most interesting. One is the uh, simple net mod demo.json. This is the introspection file, which is installed on the etc slash IP route and slash introspection. Another file, which is a simple net mod demo.template, which is also generated by P4TC, as Nihan indicated earlier. We generated by the P4TC compiler. Now we're going to install this. Okay, now you can see this introspection. Basically, the template has four tables, and the pipeline name is a simple net. And also we have actions associated with mod destination IP. That's a TX mod index action. We also install others another direction, but in this demo probably we not really the interesting that. Okay, the mod source IP table, which is we're going to modify the source IP for source net. This is a TX direction action. Then we seal this pipeline and the state now it's ready. So now we need to add a queue disk. Basically, we say we want to see the either one it's offload enable or not. We're going to set it. It was now you see the hardware TC offload is on when we set it. Then we add a queue disk. It's the port is either one associated with the uh, block 22, and we also add the filter associated with the block 22 with a P4 program. The program name it's a simple net mod demo. We are associated with this and offloaded to the hardware. As Nihan already indicated, this is uh, the previous slides they showed it. Okay, now we're gonna add one rule, which is e forwarding table. The key is 192.168.0.1. The action is a TX mod index. There's two parameters. One is ether3, which is associated the port 0, which on the link partner. Another one is the index, which is 10. It's a reference to next table we're going to enter. So now we say we're going to add a second rule on the different table. It's mod source IP table. The key is a 10. The mod block, basically it's a vendor metadata common mod block pointer. Actually, this one is a vendor specific hardware index, as Lihan indicated earlier. And the action is a mod source IP. The parameter is we're going to change the source IP address to public one. It's 10, 10, 10, 10. From basically it's from the 192.168.0.1. Actually, you can see on the top, you can see on the TC monitor, you see both table. It's inserted in the hardware. Basically, it's offloaded to the hardware. On the yellow screen, we send the SCAPI packet, which is a key, which is a 192.168.0.1, which match the first table key. It's 192.168.0.1. So once hit this rule, actually we're going to send it to the port and a reference to another mod index, which is modify the 10, 10, 10, 10 to the public IP address. Now we need to put the TCP dump on the port 0, corresponding port 0 on the IPU. Okay. Now we can see, we should see the source IP address should be changed when we send this packet. 192.168.0.1 is the source. Okay. Yes, we see this is a source IP address that has been changed, and the destination IP still keep the same, 10.10.10.11, which is web server. Source become the gateway IP address, the public IP address from private 192.168.0.1. This is the end of demo for the source net. Thank you, everyone.
Tom, you have a question?
Well, I don't want to defer break too much.
Yeah.
Can you just for 1 second go back to the slide with the code? I had a question.
That would be a challenge, probably.
Or let me describe what I saw. So there was a comment there that the checksum would be done by the IPU. And I'm assuming what that would mean is in this NAT case, we're actually recomputing the TCP or the UDP checksum based on the new addresses. Now, my concern is if that's true, this goes back to the point we made before. If we're offloading kernel functionality to the device, the behavior and the semantics of the offloaded program have to be identical to what the kernel would otherwise run. So when the kernel, for instance, is doing that, the way we update the checksum, because the addresses changes, we actually go find the checksum in the transport layer and do a delta modification. We do not recompute the whole checksum. So this is where we really need to be careful. If TC Flower fundamentally has a kernel implementation already, So if we want to claim that we're offloading TC Flower to the device, we have to somehow validate that that is a precise equivalent. Because even if it varies just a little bit, like the checksum case would probably work almost in all cases, but there are going to be cases where the semantics are slightly different, and that risks breaking users if we don't get the semantics exactly right. So I don't really know how to solve this problem, because in the case of TC Flower, we're not starting with something that's a program of it. We don't have a common ancestor like we would in the hash case. So just something to think about is if we are offloading something like TC Flower, how do we ensure that the offload is exactly what we're claiming it is, which has to be, if I offload this TC Flower command, the offloaded thing is exactly what the kernel would have done to the packet.
Yeah, I don't disagree with you, Tom.
Hear me, Tom? Am I audible? Sorry, I just want to check.
Yes, we can hear you.
Yeah. So yeah. So I mean, that's a definitely important point. I just want to clarify that most devices do the same delta update to the checksum and not recompute. But one way to make sure what is happening in software and hardware is equivalent is writing a checksum extern in the P4, and then making sure that is identical in terms of what's going on. I mean, that's the only possible way to cross-check right now. There is, yeah, that's the suggestion.
Yeah, I mean, that's true. And I'm an advocate for something called generic TC Flower that we can talk about offline, because TC Flower itself is so restricted. But there are kernel things that we're doing now, and we can go through a whole bunch, like GRO. Offloading GRO into a device is always going to be problematic, because how do you get the exact functionality? So it's a common problem. If we can solve this through a higher layer, like there's a front-end program that the kernel consumes and the device consumes, then we can do it. But offloading something that already exists in the kernel, and this is one of the reasons why we have so few kernel offloads that have been successful. It's because of this problem. The kernel is not going to trust something implicitly. The kernel would only trust an offload if it has a way to validate that's the same functionality. It's such a tricky problem with offloads we've seen time and time again.
Okay. I'm sorry, we are like 15 minutes late, and it's break time.
I'll make up for it on my talk.
Okay, right, then go ahead.
Well, TCP offload, I expect no controversy or.
All right. Okay. Okay. Well, there's a question by Jiri. Maybe just 1 minute of that. If someone from Intel wants to address that, please. There's going to be a breakout session in the afternoon with TC. I'll be more than happy to invite the driver people there as well. Anjali or somebody would like to respond to Jiri? Just 1 minute, please. No more than that.
Right. No. So I'm just good with Yuri's suggestion. We can take it up in the P4TC workshop to see if there's a better way to support the legacy hooks than what James and I kind of propose. So yeah, like if we think it is only TC Flower extension to support the actions template, and that'll do the trick, maybe that's something we can take it up rather than reinventing a new way. Yeah.
Okay. Well, thank you, everybody. I really started late and I ate some of their time. I'm sorry about that. Why? Because I'm so exciting. You know that, right? Okay. Thank you. Break time.